Hey everyone, today we are going to tackle a really cool idea in reinforcement learning, Monte Carlo methods. We're going to break down how an AI can figure out how to win a game without ever reading the instructions. Let's dive right in. So picture this. Someone hands you this awesome, but super complex new board game. You've got the board, you've got all the cool pieces, but there's no rulebook. Nothing. How in the world would you even begin to figure out how to win? Well, believe it or not, this is the exact problem Monte Carlo methods are built to solve. They're a way for an agent to learn the best strategy when the rules are a total mystery, or maybe just way too complicated to write down.
You see, when it comes to this kind of learning, there are really two main paths. On one side, you've got what's called model-based learning. This is like having the ultimate rulebook. Your AI knows every single possible move and the exact odds of what will happen next. It's like a chess grandmaster who's already seen it all. But on the other side, we have model-free learning. This is our no-rulebook situation. The agent doesn't need a map. It learns just by playing the game again and again and paying close attention to what happens. And Monte Carlo, it's a classic, powerful example of this model-free approach.
So let's get to the heart of it. To really get a feel for this, we're going to use a simple analogy that explains how an agent can learn just by playing.
Here's the game plan. You play one full game, from the very first move to the very last. At the end, you look at the result. Did you win or did you lose? Simple. Now here comes this really crucial and honestly kind of naive assumption. If you won the game, you just assume every single move you made was a good move. And if you lost, well, you assume they were all bad moves. You're not overthinking it, you're just giving credit or blame to the entire sequence. Then you just do it again, and again, and again, for thousands and thousands of times. Over time, by averaging out all those wins and losses, you'll start to get a pretty good idea of which moves tend to show up in a winning strategy.
And here's the cool part. That simple analogy we just walked through, that is the core of the Monte Carlo method. So now, let's just put some official labels on these ideas, and you'll see how it all maps perfectly to our board game.
First up, the word episode. In reinforcement learning, an episode is simply one complete run-through of whatever the task is. It starts at the beginning, goes through a bunch of actions and states, and then it hits a final, terminal state where the game's over.
So in our analogy, one full game of that board game is one episode. And this brings up a really key feature of Monte Carlo methods. They only learn after an episode is totally finished. The agent has to play the whole game and see the final score before it can update its strategy.
Next up is their return. This sounds fancy, but it's really just the total score you rack up from any given point until the end of the episode. It's the final outcome, the grand total.
In our board game, we kept this super simple, right? The return is just the final result. We could say a win is a return of +1 and a loss is a return of -1. So for every single game we play, we get one number that tells us how it went.
Okay, but this leads to a huge question. Well, sometimes called the credit assignment problem, right? We know a whole series of moves led to a win, but which one was it? Was it that great opening move, that sneaky play in the middle, or the final move that sealed the deal? How do you give credit to any single position on the board?
Well, the answer lies in something called the value function. The best way to think about this is that it's just a score for every single position or state on the board. And how do we calculate that score? Easy. It's just the average outcome, the average return we've gotten every single time we've been in that exact spot before.
Let's jump back to our game. Imagine a specific square on the board has been part of 100 different games. If, say, 70 of those games ended up as wins, that square's value score is going to be pretty high. But if another square was part of 100 games that mostly ended in losses, its value is going to be low. So we're judging a position by the company it keeps, by the outcomes it tends to lead to.
Okay, so we have all the pieces of the puzzle. We've got episodes, returns, and the value function. Now let's put it all together and see how this learning loop actually works. It works exactly like our analogy. First, the agent plays one complete game, start to finish. Once it's over, it looks at the final return. Let's say it won. Then it basically goes back in time through that game. For every single position it landed on during that winning game, it updates the average score for that position, just nudging it a little bit higher. It adds that win to the tally for each of those states and recalculates the average. Then it just does the whole thing over again for the next game, and the next, and the one after that.
A quick example is going to make this crystal clear. Let's zoom in on just one spot on our board. We'll call it square A.
So we're going to track the value of square A.
Now, just for this little example, let's make the math even easier and say a win is worth +1 point and a loss is worth 0 points. Okay, so before our next game, our agent has visited square A a total of 4 times. 2 of those times the game ended in a win, and 2 times it ended in a loss. So the total score is 2, and the average value is just that total score, 2, divided by the number of visits, 4, which gives us a starting value of 0.50. All right, here we go. We play one more game. Our agent lands on square A again, and this time, the game ends in a win. So the return for this episode is +1.
Now we update our records. We've got a new win to add to the history books. Our agent has now visited square A 5 times. Out of those 5, 3 were wins and 2 were losses. The total score is now 3. So the new average value is 3 divided by 5, which is 0.60. You see that? The value of square A inched up. It's now seen as a slightly better place to be, all because it was part of one more winning game.
Now just imagine doing that tiny little update, not once, but millions of times. By averaging over this huge amount of experience, the scores for every single square on the board slowly but surely get closer and closer to their real values. It's literally learning by brute force experience.
So why does all this matter? I mean, why go through all this trouble? Well, this is where Monte Carlo really shines.
Being model-free is what makes Monte Carlo so incredibly useful, especially when you compare it to something like dynamic programming. See, dynamic programming needs that perfect rule book we talked about. It has to know the exact probability of everything that could possibly happen. Monte Carlo, it doesn't need any of that. It learns straight from raw experience, from actually playing the game. This makes it perfect for messy, real-world problems where you don't have a rule book because the rules are unknown or just way too complex.
So, if you only remember one single thing from our chat today, please let it be this next sentence. This is the absolute essence of the Monte Carlo idea.
Here it is. Monte Carlo learning is like becoming an expert at a game, not by reading the rule book, but by playing it a million times and remembering what works. That's it. It's pure trial and error, but on a massive scale, letting you find the clear, winning strategy hidden inside all the chaos.
And that really leaves us with a pretty amazing thought, doesn't it? If an agent can master something incredibly complex just by looking at the final score, with no rules to guide it, what other real-world problems in robotics or finance or anything could we solve just by letting an agent play the game? Thanks for listening.